Hello everyone, welcome to this lecture on ordinary differential equations. I'm going to take a look at the integrating factor. So this is a method for solving ordinary differential equations. Okay, so in this lecture, firstly I'm going to introduce the problem. We're going to take a look at some first order ordinary differential equations. So I'm going to talk about the type of problems that we might see. Going to take a look at the general goal. I'm going to take a look at the strategy. So this method, what is it all about? And then step 2, we're going to get into the heart of the problem for solving these problems using integrating factors. Okay, so the things I'm going to look at will be the general form, the definition of the integrating factor. Let's call it IE. This is actually a function. We call it I of x. And we'll take a look at the approach, some of the patterns that we're going to study. So that's an overview of what I'm going to do in this video. All the examples are going to be in separate videos. So this is all about the theoretical side and just introducing the problem. Okay, so let's start a clean page. Okay, so part 1. Part 1. So we're going to work with x, which is an independent variable, and a function y, which depends on x. So y is a dependent variable, which changes according to x. Just want to say at this point, sometimes we're going to use t and x of t. This is suitable for physics problems or engineering problems where some variable, say x, changes according to time. So we just need to be a little bit flexible. Just want to highlight that at this stage. We need to really work in the context of the question. Okay, so the equations that we're working with, well, they're going to use y dy dx, also functions of x. So lots of x is mixed up in this case. Okay, so our attention is going to be on linear differential equations. So no powers on y or dy dx, and we want them separated, the y and the dy dx term. We want these separated, we don't want them multiplied together. Okay, if they're multiplied together, the equation will be linear. And x is the functions of x. Well, this could be anything. Could be sine x, cos x, sine x times cos x times log x, or all different combinations of functions, and x is everywhere. We can mix them all up. Okay, so the goal, well, of course, is to solve. We want to find what is y. So we're going to be looking, well, there's two different types of problems actually. We could have a general solution. So this is going to include all solutions. This is the problem we're going to solve really. So the answer is going to involve some constant c, which is just coming from reversing the dy dx by doing some integration. So some c is going to appear. And maybe later on we'll look at some particular solutions. So normally there's some initial condition, and then there's going to be some particular value as C. So there's one solution given an initial condition. So I'm going to focus on the first one. We're going to take a look at the general solutions. Okay, so how do these problems, how do they appear? What do they look like? Well, let's take a look at some examples. Well, we might have something like this. We could have some x's, a dy dx, some y's, these being separate terms, so we'll add them, and maybe some function of x on the right, and the goal then is find y, what is y, or another type of problem might be cos of x times dy dx plus sine of x, y equals log of the modulus of x. Again, what is y? So a few things to notice here. Firstly, the y and dy dx terms, they're separated. These are linear, so they cannot be multiplied together. Also notice the dy dx doesn't have a power on it. If we were to introduce some power here, it would no longer be linear, so we can't do that. And the x's, they can be anything. You can just dump loads of x's over here. You could put a load in front of here, or load more in front of here. The x is not the problem. We can multiply them in any of those terms. Okay, so the first question is, can we write this in one particular way? So given any problem that looks like this, first order, is linear, is there one way we can write them so we can compare different examples, compare to some of the shapes? And of course this is possible, and the way it is done is by isolating the dy dx term. So the convention is that this dy dx term stays on its own. Okay, so the general form, dy dx on its own, we have a y here. Well, we could have lots of x's in front of it, so we're going to call this p of x, and on the right hand side it could be lots of different x's, call it q of x. This is the general form. This is something that's very important. All the problems we start with, they either need to be in this form or we need to write them in this form. Okay, so let's revisit our examples, the previous examples, just up here 1 and 2. How do we write these in the general form? Okay, so what do we notice? Well, dy dx should be on its own. So we don't actually want this x squared here. So for example 1, we'd have to divide through by x squared to write it in the general form. For example 2, dy dx is here. Again, we want it on its own, so we'd have to divide through by cos of x to get the dy dx on its own. So let's take a look at doing that. Let's go to a new page. So EG1. So let's write this problem in general form. So the question is, what is P and what is Q? The two functions that appear in the general form. So like I've already mentioned, we need to divide out by x squared. So we end up with dy dx, the x squared is going to cancel, y divided by x squared, and on the right hand side, sine x divided by x squared. Well, we don't want the y and the x is all mixed up in here. We want to separate the y put that on the right, and all the x's on the left. So I'm just going to rewrite this more convenient form. I'm going to put 1 over x squared in front of the y. Okay, so now when I compare with the general form, I can see whatever sits in front of y is p of x, and whatever sits on the right hand side when dy dx is isolated is q of x. So p of x is 1 over x squared, and q of x sine x divided by x squared. Okay, so this is the general form. How about the second example, e.g. 2? Let's follow a similar process. Let's take a look at that. Oops. So e.g. 2. Just this differential equation I made up. And we want to write this in general form. Okay, so like we saw with EG1, we need the dy dx term on its own. So we have to divide out by cos of x. So if we divide every term by cos of x, we have dy dx plus sine x divided by cos x. Remember to keep that y on its own. It's quite convenient for finding p. And then on the right hand side, divide by cos of x. I'm not going to worry too much about the domain here. There's some values of x that don't make sense in this equation. I'm not too concerned with that at this stage. So the general form, we know, is dy dx plus p of x y equals q of x. So in our case, p of x is sine x over cos x. Using some trig, we know this is tan of x. And q of x is this strange looking function that sits on the right, log of x divided by cos of x. There's not much we can do to simplify that. Okay, so there you go. That's how you turn functions into the general form. It's quite important. We'll deal with this a lot later on. So let's move to part 2. Part 2 is all about solving these differential equations when they're written in the general form. Okay, so part 2. Methods for solving these ODEs. So the methods for solving. Okay, so I'm going to begin with introducing a very nice example. So in a perfect world, these problems might appear like this. We're going to spot there's something very nice about these types of problems. So we have x squared dy dx, 2x plus 2x y equals x to the power 4. So why is this so perfect? Well, there's a certain pattern that appears on the left hand side. The left hand side looks a lot like the product rule for differentiation. So how can we see that? Well, let's label some things up here. So if I start with the y's, something here and something here, So maybe I'll call this G. So if y is the same as G, dy dx is dg dx. Here I have some function, and here I have some function involving just the x's. So I can see if I differentiate x squared, I get 2x. So if I call x squared f, then this thing over here is df dx. So actually this right hand side looks a little bit like f, some function, differentiate g with respect to x, plus df dx times g, which of course is just the product rule for differentiation. Okay, it might sound like a simple thing at the moment, but this is really, really big. It's going to provide a means for us to find an answer to this problem. So the product rule for differentiation says if you differentiate f times g, well, it's the same as keep f the same, differentiate g, times them together, plus differentiate f times by g, times them together, add those two terms up. Okay, so this thing on the left hand side up here, actually this is the same as the derivative of f times g. If I just look at my labels here, f is x squared and the g is y. So the left hand side is differentiate x squared times y, and the right hand side can just stay as it is. It's just x to the power 4. So the reason why I mentioned this is a very nice example is because the left hand side is a product rule. I can rewrite it in this form, and this problem is much easier to solve. So how would we solve this problem? Well, that's quite important, so let's take a look at some of the steps. Okay, so to solve this equation, when I say solve, I mean find y. Well, we need to isolate y. Y just appears here. So I need to eliminate the dy dx, sorry, the d by dx first. So to do that, I need to integrate both sides. Okay, so if I write the equation that I have, and then I integrate both sides, I'm going to do that with respect to x. So I just need to give myself a bit more room here. So I'm going to integrate both sides with respect to x, and I know that the operations of integration and differentiation are opposite. So the left hand side, the integral and the d by dx are going to just cancel each other out, and the right hand side, just going to do some integration. So go up a power, divide by the power, plus c, and then finally to find the function y, we should have just x's involved. I'm going to divide by x squared. Okay, that's x cubed plus c times 1 divided by x squared. And there you go. There's my solution to this problem. I've just gone through the processes of isolating y after I noticed the particular shape of the product rule, and everything was very convenient here. In the real world, of course, it's not going to appear as a perfect product rule on the left-hand side. We're going to have to do a little bit more work to get to that. This is one that works particularly nice. And it's a nice place to start to get a feel for solving problems of this nature. Okay, so let's look at a more realistic one. So what about something like this? 1 over x dy dx plus 2y divided by x equals e to the power minus 2x. So how about this one? Well, if we begin to study the left-hand side, well, it's quite hard to spot some patterns here, particularly in terms of using the product rule for differentiation. It's not obvious at this stage, but I'm going to give the answer, and later on we'll look at how to actually to calculate this for ourselves. The answer to this question is multiply both sides of the equation by x e to 2x. So where does this come from? Well, we'll see later where this comes from. So let's just do it for the moment. So multiply both sides. We get the 1 over x and the x cancels. So we get e to the 2x dy dx. Again, the x on the bottom of the fraction and the x on the thing will multiply and by cancel. So we get 2e to 2xy. And on the right hand side, we have just an x. So why did we do that? Well, take a look what we now have. We have some function here, e to the 2x. What do you get if you differentiate this function? So the power is going to go down by the power, the 2x you differentiate to 2, that's going to come down. That's exactly what appears here. So actually, we have a function f here, we have its derivative here, df dx, and similarly we have some function g and dg dx here, and like before, everything's very nice. The left hand side is the product rule, f times g, which is e to 2x times y, and the right hand side just stays as it is. And we can use the same method as before to isolate the y. Okay, so the most important thing of this problem is, where did this come from? How do we actually calculate this? So let's begin to take a look at this next problem. Look at this next. Okay, so the general problem, we've already seen the general form. dy dx p of x y is q of x, and we want the product rule to appear on the left hand side. And the way we're going to do that is we're going to multiply through. We're going to multiply both sides by some function. So that the left hand side is it has the pattern of the product rule. So the left hand side is essentially the product rule for two different functions. So this thing we're going to multiply through by is called the integrating factor. So the function we're going to multiply both sides by, this function is called the integrating factor. And I'm just going to let ix, so just the function, be the integrating factor. Okay, so if I do that, so I'm going to take this equation here and I'm going to multiply by Ix. I have an equation that looks like this. Okay, and we want this to be, so I'll write this a different color. We want this to be d by dx of f times g. So we want to see df dx times some function g, f times dg dx. This is what we want to see. Okay, so next we need to start looking at patterns on the left hand side. So we can see there's x's and y's in those terms. It's easier to begin with the y's. We can see a y in the second term and a dy dx there. So that's quite nice. We could call this one, say, g, this one dg dx. Take quite a nice form. The next bit is maybe not so obvious. Okay, so we want to build some function f. So if I call, say, this one f, and I want to see its derivative elsewhere. So the derivative should be here. Oh, df dx. Okay, so this is what I want to happen. For this to happen, so here's the tricky bit. For this to be true, I need this function here, so ix px, to be the derivative of this function here, I of x. And this is the hard bit. So the requirement is for the left hand side to be the product rule, that the derivative of I, which is this one here, must be the same as this one here. So let's take a closer look at this condition. We require di dx to be I of x, p of x. Okay, so can we find I of x from this equation? And it turns out we can. We use a method called separation of variables. So this involves putting all the i's on the left hand side and all the x's on the right hand side, and integrating with respect to x. Oops. So I'm going to integrate both sides with respect to x. So let me just highlight what I'm doing a bit clearer. I'm going to integrate this with respect to x, and I'm going to integrate this with respect to x. The dx's cancel, so integrate 1 over x, sorry, 1 over I with respect to I. This is log of I, and this one just stays what it is. Don't know what p is, depends on the question. Integrate it. I want I on its own. Opposite of e, so the opposite of log is e, so take e of both sides, and I have an equation for my integrating factor. Here's the definition, here's the important thing. The integrating factor is e to the power integrate p of x. This is absolutely key to solving these problems, calculating this integrating factor. Right, so let's round up. Where are we with this? So we have shown that if we start with something in the general form, we should multiply through by the integrating factor. And the left-hand side will always appear as the product rule of the integrating factor times y, and the right hand side is always q of x times by the integrating factor. So to solve, to find y, we're going to integrate with respect to x, just like we did with the previous examples. So let me write it first and say a bit more. So what we're doing, we're going to isolate the y. To do that, I need to reverse this d by dx. So I need to integrate. That's exactly what's going on over here. The opposite of integration is differentiation. So I'm left with I of x times y on the left hand side, because all these symbols just cancel off. Integration, differentiation, opposite. The right hand side is just some function. I don't know what it is. I don't have any specific functions to deal with at the moment. It's just the integral of I times q. So my answer is wherever you get from integrating I times q, divide that by I of x and plus c. Here's my general solution to these first order differential equations using integrating factors. Okay, that was a lot of work, a lot of different ideas in there. So let me just summarize the steps you need to follow when you're solving these problems. All the ideas have been discussed, so this is the approach you should be following. Given a linear first order ODE, write this in the general form. You're going to pick up a few marks in an exam or some assessment. This is your general form. Step 2. Calculate the integrating factor. You should know the integrating factor is the integral of p of x, and then we put that in a power of e. Step 3. Okay, we saw the whole idea of the integrating factor is we multiply the general form by the integrating factor, and something nice happens. So multiply the general form by I of x. In your case, you're going to have some functions to deal with. In my case, I'm just using p's, q's, and i's. Step 4 is all about spotting patterns. This will always work. The left hand side will always be the integrating factor times y that appears inside some derivative, and the right hand side is just the q of x, where the x is isolated, multiplied by I. And step 5, you integrate both sides of step 4 and rearrange for y for your answer. Just before I finish, a few things to highlight in terms of constants of integration. Here, when you integrate p, don't add on the constant of integration. We're not trying to find some general solution here. We're trying to find something that works. In your final answer, add C. This is the opposite. We are trying to capture all the different solutions. So if you add the constant C at the end, that will deal with the overall goal of finding the general solution. So there you go, lots of ideas. This is one very powerful technique for solving differential equations. Check out some of my later videos where I go through lots of different examples. At the moment this is very theoretical. Once you've done a few examples, all of it tends to come together quite nice, normally quite quick as well. Okay, any questions, leave me a comment. Otherwise, see you in the next video. Bye bye.